All right, should I start, Adrian?
One sec.
Okay. You give me the go.
All right. Welcome, everyone, to our Quantum Matter seminars. My name is Adrian Fagin. I'm your host. Today, we have a great pleasure to present Immanuel Bloch from Ludwig Maximilian University and Max Planck Institute in Quantum Optics in Munich, Germany, who's going to be talking about cold atom experiments and his studies of quantum matter under the microscope. Thank you, Immanuel, for being here with us. Please go ahead.
Well, thanks, Adrian, and it's a real pleasure to be present in this new virtual format. Of course, it would be great to see you all in person, but I guess this is the best we can do for now. Yeah, so I would like to tell you a little bit about our experiments on quantum matter under the microscope. And oops, let me see. Okay, so here we go. And basically what I want to concentrate today on is our experiments on the Fermi Hubbard model. So we have a lot of experiments going on, but today I want to focus on the quantum gas microscope experiments on the strongly correlated Fermi Hubbard model. Tell you a little bit about how we detect the system, how we can probe interesting effects in low dimensions, and maybe something very new in the end. I want to explore actually how this system, this two-dimensional system, evolves as we continuously dope it away from half filling and basically observe transition from a polaronically dominated quasi-particle behavior to Fermi liquid behavior. So I think this is very new, and I want to just share this. This has not been presented before, so I'm excited to share this with you and get some reaction from you on this very new part also. So let's get started. For those of you who don't know at all what we're doing, who've never heard what we're doing, so we're basically creating artificial quantum matter in crystals of light. By interfering laser beams, we can create interference patterns like this beautiful one created by Ted Hensch in his labs in Munich by interfering 5 laser beams, this quasi-crystal structure that you see here. And basically what we do is we just load extremely cold atoms into these very feeble potentials, and they basically experience this as the potential landscape they move in. And then
Immanuel, sorry to interrupt, but I think your slides are frozen.
My slides are frozen. That's not good. I see them moving. Let me try again. Do you see my slide actually?
Now I do. Mm-hmm.
Okay, let me try again. Do you see this now?
Yes, I do. Mm-hmm.
Let me switch. Do you see this atoms coming now, or?
I see a nice diffraction pattern.
Yeah, but you don't see it. Did you see it changing now?
No, it's not moving.
Okay, that's not good. Okay, obviously that's not good. So basically, then let me stay in this this mode here, and we'll just. You see now you see the changes, no?
Yes, I do. Mm-hmm.
Okay, sorry for that. I don't know what's going on, but let me try to make it bigger here. See if I can get rid of this. Okay, so let's just do it like this. Let me try one other thing, maybe. Let me try this. Do you see it changing now?
No.
Okay. Why is it? Resume share. Wait, moment. Maybe it's sharing is pause. Bring your shared window to the front. I thought I did that. Wait a moment. Let me try to share the window. Share again. One moment. Let's try this. Okay. Do you see the window? Do you see it now?
Mm-hmm.
Do you see it changing?
Yes.
Okay, great. Okay. Perfect. So here's the interference pattern here.
Oh, now it's moving. Now it's moving. Yeah, everything is.
Okay. And here are the atoms we load into this interference pattern, and then we basically study their behavior, and that's all what I'm going to tell you today about. And we can do this with bosons, fermions, or mixtures of both. So really in quite a variety of systems. We're not constrained to spin systems, so we can directly study fermionic particles in these systems. Okay, so the tools of trade that are important for us today is this quantum gas microscopy that allows us to take photos of these systems. And just to remind you what this allows us to do, because it's really a fantastic new detection technique for us, that basically we can take a many-body quantum state psi, and which is a superposition, for example, of different configurations of those particles. And when we take a photo of the system, we do this with single site resolution and single particle sensitivity. So we can basically detect on a given site how many atoms there are, for example. So if we do such a measurement, we collapse the wave function onto one of those configurations, which one, of course, we don't know. That's completely random. with a probability given by the complex coefficients norm squared in front of this configuration. And that's what we see in a single shot. And then we prepare psi again. So I hope you see my cursor. So here you prepare psi again, you measure again, you collapse onto a different part of the wave function. And you do this many times, thousands of times, 10,000s of times. And at the end of the day, what we get is we get probability distributions of configurations of those configurations. And those allow us basically to access non-local correlation functions beyond what is typical of those configurations. And those allow us basically to access non-local correlation functions beyond what is typically available in standard condensed matter experiments. So we can ask questions, for example, as we'll see in the talk, how is this particle here correlated with 2 over here, conditioned on having a hole in between? So that would be, for example, already a 3-point correlation function that you couldn't access in standard condensed matter experiments. And we'll see actually throughout the talk, especially at the end, that this makes quite a difference. A lot of the features of the system only reveal themselves when you go to these higher correlation functions. So here's a picture of this showing how this works, and similar pioneering experiments have been done in, for example, in Markus Greiner's group in Harvard, where you can basically see when we load atoms into a single plane here of this lattice, we now detect them by shining light on them, and then we can see those individual atoms appear in the microscope. Each of those atoms is a bright spot showing up where the atom is in the crystal of light in the lattice structure that we're seeing. And you can see we can do this with a really high spatial resolution. We can also address the spin states of the particles or move them around to positions where we want to have them, or introduce holes or defects at positions where we want. This just shows you how well we can manipulate those systems. So we can, for example, arrange those particles on the lattice, which has 0.5 micrometer separations with 50 nanometer resolution, and, for example, order them just as a fun example, make a psi out of them, out of 26 individual atoms, just to show how good the spatial control is that we have over those particles, and do spin manipulations on those particles. One thing we're using a lot now in the experiment is using these digital mirror devices. So this is a micro mirror array out of millions of very microscopic small mirrors that you can turn on and off. You can tip and tilt these mirrors by giving electrical pulses to them. You can basically program arbitrary light patterns to be shown onto the atoms. This is basically what you have in every projector, because of course here we project these light patterns as potentials onto the atoms. So you could make a line of light or a tunnel barrier. You could make more exotic lattice structures. You could make 2 wells where you fill one well with atoms, let the atoms flow through this wire of light into the other box, basically to study conductance through this quantum wire. Or, you know, if you don't want harmonic trap potentials, you can really just do box potentials, as you can see here. So this is what we're using actually a lot right now. We have to fight a little bit the speckle that comes with coherent light to try to get very good potentials, but we're doing reasonably well. And I just want to show you a recent example of what we're doing to, for example, create ladder systems. So this is on the left, you see the pattern we program the micro mirrors to be. So whenever you see a white pixel here, it means that mirror is tilted, is turned on. And when it's black, that mirror is off, basically. When we shine light onto this DMB pattern, it gives us this light field. This light field, the atoms experience is the potential. And we basically can have a lattice structure on top of this potential. And now you see we get this really nice box potential with these ladders, quantum ladders, these Hubbard ladders in between. So these are actually fermions in here in this system. And you can see the nice ladder structures they're forming. By decreasing the barrier height between the ladders, of course, we can also continuously couple them, go over from the ladder system, for example, to the 2D system. So this is a single shot when we measure the atoms, and when we repeat this and measure the average densities, you can see we can really create nicely homogeneous ladder systems without the harmonic confinement present in the system. Just to give you an idea of what we can do. So let's turn to the focus of today's talk is the Fermi-Hubbard model and the interesting physics that's going on there. And I took this phase diagram from Bernhard Keimer's review paper on this, showing like the many interesting phases that are going on. We're mainly going to be up here in the temperature regime. So we're not down here. We hope to get there, down there, or wherever down there means, actually, how cold one has to get to see many of these very interesting phases down here. But we're in a regime where we can see antiferromagnetic order, and I think where we can see as you'll see some of the interesting physics going up here in the system. And in the end, what we want to answer with these experiments, with this unique microscopic access that we have available, is how is the interplay of dopants, which can be, excess particles, atoms we put into the systems, or holes that we put into the system, how do they interplay with the magnetic order that we have in the system, in the undoped system? So I think this is the key question that we'd like to answer. And one thing I'd also like to point out already that is interesting, we can change the doping continuously, going from basically zero doping to almost 80–90% doping. And this is for us just a continuous variable, as you'll see at the end of the talk, that we can change and see how these different correlation functions in the system change. So there was a real breakthrough in 2016-17 with a host of experiments on these quantum gas microscopes for fermions that allowed people to study this Fermi-Hubbard model. I've listed here a few. I mentioned Marco's experiments in Harvard already, beautiful experiments at MIT also, and in Princeton. So really this opened a whole new window of exploring a Fermi-Hubbard model with these quantum gas microscopes. Here's a very nice result from Markus Kreiner's group in Harvard in 2017. Where they realized in a 2D system with spin up and down fermions, fermionic atoms, a nice antiferromagnetic correlation. So in the undoped regime, where we're somewhere here, we are in a regime where we have nice antiferromagnetic correlations. And the way to see those correlations, what Markus did in the experiment was to basically remove one of the spin components from the system. So you have up and down spins. If you measure the fluorescence of them, you see both spins and you don't know where the spin up and downs are. But if you want to know where the spin downs are, you basically remove, for example, this, you want to know where the spin ups are, you remove the spin downs and you're left with the spin ups. And every time there's a hole, you know that's a spin down particle. Okay, so every time there's a hole missing, you know there's a spin down, and you can see really that gives you this nice checkerboard antiferromagnetic correlations that you can see. But of course, also what one should say, of course, that this works nice if you're in the undoped regime, but if you're in the strongly doped regime, this method does not work anymore because you cannot distinguish whether this hole that you're seeing here is really a dopant or is just a spin down particle that you remove. So this works nicely in the undoped regime, where you can see nice correlations as large as the system size, antiferromagnetic correlations. But for the doped system, you need to do something different. So I want to explain a new technique that we introduced last year that was just published recently on how we actually can detect in such a Hubbard system both spin up, down, holes and doublons in the system in one single shot, one photograph of the experiment. And the way the system, and the general idea is that we split the system, this single layer, into two layers, where the upper layer is only occupied by the spin up particles. The lower layer is only occupied by spin down particles. We separate them over large enough distances, and then we subsequently take photos of the upper and lower layer. So here's kind of a sketch how this would look. This is kind of your 2D system, just one configuration it could be in. Now you do this splitting, and now you move your lens into focus with the lower plane, you take a photo. Then you move your lens into focus with the upper plane and take a photo, and now you get a photo of the spin ups. And then you can put them both together and get a full image of the spin and charge distribution of your system, like a single snapshot. I just want to show how we actually do that, because it actually involves nice topological physics, a Thouless spin pump, actually, how we actually split those layers. So imagine you have one layer, one of those layers, being represented by this well that I show here. And we have a lattice structure on top of that. But since we only have one 2D plane, we only have one filled layer. So the 2D plane extends out of plane of your screen. And what we basically do now is we apply a magnetic gradient field. We introduce a short-spaced lattice which splits each of those large wells into a double well. And by making use of the fact that the two spin states have opposite magnetic moment, we basically pull the two spin states into opposite directions. So now the spin downs are in the left well of the double layer and the spin ups are in the right well of the double layer. Actually in Z's, in vertical space, it would mean they are now occupying adjacent vertical layers of our optical lattice. And then we apply this charge pump. So we apply this modulation of the lattice potential by changing the frequencies and amplitudes of the lasers involved in creating the super lattice. And by doing that, we can we can increase step by step the separation between those two planes. And remember, originally, these were the spin down atoms, and these were the spin up atoms, for example, in my system. If I take a photo from the side, what you actually see that indeed this single layer that we had initially is now split into two layers, where one of them are the spin up atoms and one of them are the spin down atoms, but now they're separated by a really large distance, and we can nicely photograph them independently. And here are some examples of that. So here's the upper layer showing you the spin up atoms. Then the lower image is the spin down particles. And by putting them together, we get the full configuration of the system. So now we get a full map of the 2D systems, knowing where the spin downs are, the spin ups are, the doublons are, the holes are. So it's like if you're a Monte Carlo person, it's like getting a single snapshot from your quantum Monte Carlo simulation. But of course, this is not the simulation. This is really the real experiment showing you one of the configurations of the system that you get in one of these measurements, actually. And we see this preserves nicely the antiferromagnetic correlations. So this whole detection process is really as non-destructive as it can be on the correlations, and it allows us to employ this also on these 2D systems. Actually, using this technique, we can also look at bilayer physics, but today I don't want to talk about these bilayer experiments. So I want to actually switch gears now and talk about first experiments in one dimension on spin charge separation, and then turn to the 2D experiments. So you know that one of the hallmark experiments of fractionalization that you have in condensed matter physics occur in the spin 1/2 Hubbard chains, where if you inject a spin 1/2 particle or remove a spin 1/2 particle, an electron from the system, you get two quasi-particle excitations, one the charge, the holon, and one spin 1/2, the spin-on particle in the system. And they are deconfined. They can basically propagate independently through the system. And the question is, can we see that with these real space images and the real time evolution that is available to us? So here's the 1D system. So this is our just standard 2-point correlator when we make one-dimensional lines, undoped in this case, zero magnetization, and we see this nice antiferromagnetic correlations for the 1D Hubbard system. Just a single snapshot how this looks. And now we're going to basically focus one laser beam onto one of those sites and basically kick out one of the particles. And then, of course, what happens in this cartoon picture that I guess you've all seen before is that you create these two quasi-particles, the spin-on, the spin 1/2, and the charge-on, the holon, moving independently from each other. Now, one signature that you've created those two quasi-particles is that they move at different propagation velocities. The spin-on, of course, moving at exchange kind of energy scales, and the charge-on, the holon, moving at tunneling energy scales, which are much larger. In our case, maybe a factor of order of magnitude different between them if u over t is a factor of 10, for example. I should say, of course, there have been these beautiful experiments, for example, in Amir Jacobi's group, who looked at this phenomena of spin charge separation spectroscopically. But it was noted, I think, early on in DMRG simulations that that you could actually, if you would have this local access I talked about, that you should be able to see this actually directly in the experiment. And here are some is a work from Willi Zwerger, Corinna Kollert, and Uli Scholwerk, who were one of the first who did these simulations in this respect. So here I show you some data on this. So here's the upper graph is the hole density. So the x-axis is the position on the chain. Vertical axis is evolution time in tunneling times. And you see when we create a hole at time t equals 0, we create it localized, pretty localized on the site where we focus our laser beam. And as it spreads out, as time moves, we see the hole density evolve, and you see it shows this interference structure, which is just basically the quantum walk occurring from the holon on the lattice, basically. And the interference structure shows you that's actually coherent motion of this hole on the lattice. For the spin part, we can look at the next neighbor spin correlator, the C1 spin as Z correlator across the hole, and then start to see how actually the excitation we make also spreads out in time. You see, we don't see an interference structure here, but we see some spreading of this correlations that we have in the next neighbor spin correlations in the system as well. And now, just in order to assign a propagation velocity to these, we can take the fastest velocity. We can just take this cone. We can try to, extrapolate a whole width of this distribution function and measure this width of the evolution function as a function of time. And then you see, indeed, those two excitations have completely different velocities. The red curve is the holon density spreading. The blue curve is the spin part spreading. And you indeed see that this agrees nicely what we expect from theory, the gray basically boxes. And the difference is basically what we expect also from our U/T value. Now, seeing just different propagation velocities does not prove fractionalization. But I would like to show you that by accessing these higher order correlators, we can have a much better access to what's going on in this fractionalization process and maybe help to understand how these are really nice ways of observing these phenomena. So one correlator you could look at is this 3-point correlator I wrote down here. It's a spin-hole spin correlator. So it correlates the spin on side I-1 with the spin on side I+1, conditioned on having a hole in between. So we're asking, how is the spin environment around a single hole that we have in the system? And you basically see, if we start with a basically antiferromagnetic, Heisenberg chain, undoped or filled, and we just remove one particle at time t equals 0, this correlator will be positive, because these spins tend to be aligned. But as the spinon separates from the holon, as the spinon moves away from the holon, you actually see that as time evolves, the spin correlator around the hole now actually will turn negative because the spinon has moved away from the holon. And this is indeed what you see here. This is the spin-hole spin correlator. It starts out positive, and then as time evolves, it actually turns negative and then settles onto kind of a background value that we have in the system. So this is a much more direct way of showing this fractionalization going on, the spinon part really being removed from the holon and the holon just turning to the background value we would expect even for the ground state, as we'll see in a second. You can look at also magnetization fluctuations. So you can ask, actually, if you sum up the SZ values within a certain region of space and take the absolute value of them, or the square of the sum of the magnetization in a certain region, you can look at magnetization fluctuations, thereby also reveal how the spinon is spreading in the system. So here I'm showing the red curve is basically the undoped Heisenberg system, where you basically have magnetization fluctuations in the system already simply because of quantum fluctuations and of thermal fluctuations. But now when we remove one particle, you see you get this excess hump here. You get an excess spin fluctuation in the system, just the spin basically you remove. So you have excess magnetization fluctuations. And as time goes on, you see that they spread out. And if you subtract the red curve from the blue curve, you can basically get an idea of the spinon spreading, which is what you can see here on the right part of the system. Also, a non-local, highly non-local correlator that you're measuring here, basically the fluctuations of the system over a finite region in space. So let me just connect this to actually an interesting hidden order in the ground state of the system that one can find that is even present at t equals 0. So everything I showed you so far was a dynamical experiment where we took the chain, we kicked out a particle, and we dynamically try to see how the system evolves and see how these correlation functions change. But now I want to ask, how does the system behave at t equals 0 when you dope it? So no dynamics, it's the ground state we're talking about in the system, and we're trying to find out what it should look like. And basically we have two competing requirements that we want to fulfill to minimize energy in the system. Holes, as particles, want to delocalize to minimize their kinetic energy. Spins, on the other hand, want to align antiferromagnetically in the system to minimize exchange energy cost. And the best way you can do that, if you, for example, have a single hole in the system, is actually to go into this left configuration of the system in this cartoon picture, where basically around a hole, you have antiferromagnetic correlations in the system, and the hole is delocalized over the entire system. So your many-body state is a superposition state of the hole being everywhere, completely delocalized, minimum kinetic energy, but the neighboring spins adjacent to a hole should be antiferromagnetically aligned rather than ferromagnetically aligned, what you would expect if you just kick out a particle from the system like what we saw before. And you can actually show this, this picture of a hole actually extends to the whole system, where basically if you look at the antiferromagnetic order, a single hole is like a domain wall for the parity of the antiferromagnet. So if we call the parity of the antiferromagnetic order the way which these spins order on the sublattice, so if it's like down, up, let's call this order +1. If it's up, down, let's call this order -1. And like each time we introduce a hole in the system, we basically flip the parity of the antiferromagnetic block adjacent to this hole. So this hole really is a non-local topological excitation to the system. It infects the entire system whenever you introduce a hole into the system. And here's actually here's a picture experimental data that you can directly see that. So let me walk you through this slightly complicated plot. So again, we're looking at a 3-point correlator. We're measuring the spin on side I correlated with a spin on side I plus D. So let's say this spin here with this spin over here, conditioned on having a hole at side I plus S, where now S can be either larger than the distance of the two spins, so the hole lies outside of the two spins you're correlating, or S is smaller than D, so the hole lies between the two spins that you're actually correlating in the system. And as I told you, that makes a big difference, because whenever there's a hole, the parity should be flipped. And this is actually shown in this experimental graph. So here's the distance between the two spins. Here's the position of the hole. Whenever S is smaller than D, the hole is between the two spins, and we get one type of antiferromagnetic order, let's say blue, red, blue, red, blue, red, blue, red. But when we go S larger than D, you see that everything was blue turned into red, and everything was red turned into blue, showing that the correlations have precisely been flipped. So the parity of this antiferromagnetic order has been flipped. You can show this even nicer if you take out the staggering, of the antiferromagnetic correlations by introducing the -1 to the power of D factor into the system. And then the positive value would mean here red one type of parity +1, and the blue value would mean another type of parity -1 parity in the system. And you see that this hole really changes the entire parity of the antiferromagnetic block in the system. We can also connect that now, if we dope the system with more holes, we can basically apply the same principle that each time there's a hole, we flip the block of spins. And if we stare at such a picture, we can also understand what's going on by basically going into a fictitious squeeze space where we would remove all the holes in the system, and then basically find that the resulting system we get shows nice antiferromagnetic correlations like an undoped chain. So this antiferromagnet, in a sense, is hidden from us. If we only have access to 2-point correlations, we would never be able to tell that there is an antiferromagnet, because I've correlated this spin with this spin over here. We would always get vanishing correlations if we have fluctuating number of holes in between. But if we know the number of holes in between, I can predict what, if I find this spin up, I can predict what this spin is going to be like. Okay, and this is, of course, can be captured by this famous string correlator. That's, of course, very well known for the spin 1 Haldane chain. Very similar thing here. This thing, the correlator, the part in between, just counts the number of holes in the Haldane chain. It counts the number of zero spins that are between your endpoints that you're correlating in the system. In the end, the fact that this is non-zero value for this Hubbard chain goes back to actually a very, very nice result known from Bethe-Ansatz on spin charge separation, that the many-body wave function we have in the system can actually be written as a product wave function of spinless fermions defining the position of our electrons on the lattice, multiplied by an antiferromagnetic Heisenberg part on this fictitious squeeze space lattice, on this squeeze space lattice where all those electrons have been removed, the holes have been removed from the system. And now you see actually this spin charge separation that we saw dynamically actually takes a very nice form in this many-body ground state wave function, actually showing this factorization into this density part and the magnetic part for the ground state of the system. So the spin charge separation manifests itself in a very fundamental way in the ground state wave function of the system. And let me show you that we can really measure this. So this is the 2-point correlator measured over different degrees of, this is what I want to show you. This is the 2-point correlator measured over different systems where the doping varies between 20% and 80%. And actually you see only when the spins are right next to each other, when there's no possibility for a hole to squeeze in between, we get antiferromagnetic correlations. But as soon as we go to larger distances, because we can have this fluctuating number of holes in between, you see immediately that this correlator becomes flat and there's no spin correlation anymore. And well, if you are an experimentalist and you see this data, I think the only thing you could conclude that there's no magnetic order basically in the system. But if we evaluate the string correlator and measure the position of the holes as well, or go to squeeze space, then we can indeed see that we can recover those antiferromagnetic correlations in the string correlator and show that there indeed is an antiferromagnetic correlation hidden just from us in the system that we can reveal through these higher order correlation functions. All right, so let me switch gears from 1D to 2D now, making things a bit more complex. Is of course all well understood theoretically, but I would say still nice that we can really see this in the experiment in this direct way through these non-local correlators. And I think it also gives you kind of an idea what kind of nice things you can measure here with these non-local correlators. So I want to start now with a 2D system, go to a 2D antiferromagnet and ask similar questions. What do impurities, dopants do in this 2D antiferromagnet? And the simplest question you could of course ask is, what does a single hole do in this antiferromagnet? Yeah? And this is of course a Gedanken experiment for any real condensed matter experiment, but not for theory, of course. And very famous people have worked on this. I just picked this famous paper from Charlie Kane, Patrick Lee, and Nick Reed, having looked at this problem already in 1989. What I want to say is that we can do these experiments now by looking indeed at single dopants and their effect on the antiferromagnetic order in the system. So what's different from 1D? Well, again, you have this competition between magnetic and kinetic energy. But in 2D, of course, if the dopant, and now I choose a doublon rather than a hole, but it would be the same thing for a hole. If it moves around, it of course leaves behind this string of flipped spins. So this is already different because as the doublon moves further and further, you have more and more magnetic energy cost to pay in the system. And so you cannot have this separation between the doublon, for example, here, and a spinon, for example, as you had in the 1D case. So the situation is fundamentally different. And what happens, of course, in the 2D system is that you form a new quasi-particle, that you form a polaron, a spin polaron, where the magnetic correlations are distorted around the impurity that you introduce into the system. In the extreme limit, of course, you can have a situation where, within this vicinity of this impurity, you can have ferromagnetic correlations where now the hole or the dopant can move very easily, basically unrestricted in this regime. Yeah? So, and then of course, this hole can be everywhere in the system, the polaron. So in the end, you have a superposition of this distorted spin background being everywhere in the system. And that's basically what happens for a single dopant that you would put in the antiferromagnetic background. What's the size of such a system? Well, already if you go to Asser's book, Asser Auerbach's book on quantum magnetism, you can do this simple calculation that even I managed to do by competition of kinetic and magnetic energy cost, and you find that the radius of this spin polaron is basically given by the Baire hopping to the exchange energy to the 4th root. So very weak dependence on T over J. In a slightly kind of more advanced picture that, for example, Eugene and Fabian Groß developed using spinon-holon binding, a string between them, you find this is kind of in a more refined version, T over J to the 1/3 power scaling, but still rather weak scaling. And we expect kind of a small object to appear in the system for realistic T over J values in the system. Okay, so here are pictures of actually indeed seeing this spin polaron in the system. So let me explain you what you're actually seeing here. So we take photos of the 2D system. We dope it, for example, with doublons. And when we make a photo, this doublon will appear completely random positions in the 2D image. We don't know where it's going to appear. It's going to appear somewhere. But then we can look at the spin correlations around that doublon. We repeat the experiment, the doublon appears somewhere else, but again, we can look at the spin correlations as Z correlations around the doublon. So what you're actually seeing here is a 3-point correlator plotted in this 2-dimensional plot. We recenter our coordinate system on the impurity. So this is the doublon that we have here. And we measure how the spin correlation, for example, of this horizontal bond distance basically 1 away from this doublon is affected by the impurity compared to the background. So when you go far away from the impurity, you see you have the standard antiferromagnetic background, the white, but you already see that in the vicinity of this doublon, you see the distortion of the magnetic background. The magnetic correlations are actually changed. Actually here, the antiferromagnetic correlations are reduced. You see they're stronger in the background. They are reduced here for this bond here, for this horizontal bonds or vertical bonds that you have. This is even more striking if you look at diagonal correlators. If you look at the diagonal correlators, which would of course be ferromagnetic in the undoped system, if you look around the doublon, actually they completely change sign. Yeah? They completely change sign and have a dramatic effect by this mobile impurity that we have in the system. And one thing I didn't have a chance to explain now is that really the mobility of the particle is crucial to see this. If you would have a static impurity, you would not see this distortion of the magnetic background. So the mobility of this impurity is crucial for seeing this distortion of the spin background in the system. And we can do this over larger distances. And I think what I want to say that, you know, if we want to now compare the theory and also in the end distinguish between different models, as I'll come to in the next part of the talk, we want to be, from an experimental point of view, as model independent in our analysis as we can. So I don't want to favor any specific model in my analysis. I don't want to be biased at all in any way. And I think by measuring just purely correlations function in the system, this is as unbiased as we can be. Now, we're just evaluating correlations between the particles, and that's what I'm also going to show you in the next part. So new part now, the new stuff that I'm excited to share with you. This is now what happens when you continuously increase doping from these very few dopants where you have polarons to like 80–90% doping. So we're now in a regime where we will go on the doping axis from very low doping, where we have polarons as we just saw, to this extremely strong doping regime, where we also know from actually both condensed matter experiments and quantum Monte Carlo simulations that over here, the nature of the quasi-particles is completely different. Over here, we expect something that is more Fermi liquid-like, whereas over here, we remember we have the polarons in the system that I just showed to you before. And now I think the really nice thing is that we can really go at this continuously as a function of doping. And now what I want to show you in the next graphs is an analysis of 2-point, 3-point, and 4-point correlators. And I want to determine the point where of doping, where the system crosses over from polaronic behavior to Fermi liquid behavior. Okay, so that's my goal in the standard Fermi Hubbard model, in the plain vanilla 2D Fermi Hubbard model, and what we can see. So we will look at these different correlation functions: 2-point spin-spin correlations, 3-point hole spin-spin, and 4-point hole spin-spin correlation functions. And all of them, as I'll show you in the end and summarize, will lead us to see that basically what we observe in the experiment is a breakdown of the polaron quasi-particle picture, change over of the susceptibility, the magnetic susceptibility, into the one of a Fermi liquid at a certain doping. We can see that also as a change in the spin density wave in the system. And when we have two holes next to each other, we can see actually strong singlet or antiferromagnetic correlations forming between those two holes, which we know from TJ model simulations is a characteristic for binding of those two holes to each other. Okay, let's start with the 2-point correlator, the spin-spin correlator, the one that's most standard, the one that you also measure in condensed matter experiments. So this is the upper graph. Again, we measure spin-spin correlations in real space, and now I just Fourier transform them. And I hope, of course, as we make system sizes larger, these features will get much finer resolved. But I think already you see the most important features. We start with the peak at pi, showing the antiferromagnetic correlations. So this is doping here, 7%, 20%, 35%, 50%. And you can see actually already that as we increase the doping in the system, that this structure factor distinctly breaks up from the peak at pi into peaks moving to pi0 and basically 0 pi. These peaks that you can see here, these 4 peaks that you can see so here. Another thing we can extract from the 2-point spin correlation function is the spin susceptibility. So by looking at the fluctuations of the spin in a finite region, we can measure the spin susceptibility, and we can measure that as a function of doping also in the system. So here you can see the spin susceptibility derived from the 2-point correlations as a function of doping. And you see basically, well, it slightly increases or stays constant within experimental error bars. And then certainly around 30%, at this pretty much the same point where we see this spin structure factor changing, we see a change in susceptibility just going down. And this just decreasing susceptibility is, of course, also something we expect from a Fermi liquid. The pink line here is a non-interacting Fermi gas, where the non-interacting Fermi gas would lie. And you see, as we increase doping, we are approaching this kind of limit of non-interacting Fermi liquid, basically. But pretty much clear, distinct change in behavior around 30% doping of the system. We also see that if we look a bit more refined now in the different correlation functions. So this is again complicated, so let me walk you slowly through this. These are spin-spin correlations. This is the spin-spin correlation between diagonal spins. This is the spin-spin correlation between horizontal spins, distance 1, distance 1.4 here. These are these next neighbor correlations. These are the diagonal correlations. And then we just increase the distance. We have distance 2, we have distance 4 basically here. And then we have these larger distances that we put into the system. And now we can compare two different theories. Well, let me first say experimentally what we see. Experimentally, if you look at these higher correlations, you see that they seem to be turning into an oscillatory behavior as a function of doping, which is again on the horizontal axis that you can see here. And we're comparing to a few different theories. We can do exact diagonalization for very small system sizes, 4x4, this uniform RBB state, pi flux state, or the string theory states. You see already some of them we can say is better agreement in the experiment, some of them worse. But I would say one limitation of the 2-point correlator is a lot of the theories give very similar results in the 2-point correlator. So it's not very differentiating just looking at the 2-point correlation functions. So let's go one step further. Let's go to the 3-point correlation function. So this is the whole spin-spin correlation function. And now what I'm looking at is the connected part of the correlation function. So it's telling me how much is this whole spin-spin correlation function modified compared to a simple antiferromagnetic background. So we take the spin-spin whole correlation function and we subtract from it the bare correlations we would get from a normal antiferromagnet. So what you're seeing in the graphs is the connected correlator, and it shows you how much these kind of bonds or these magnetic correlations are changed compared to the antiferromagnetic background. And what you see here in the low doping regime is exactly the picture of the polaron I showed you in the beginning. Remember, this bond actually, which is ferromagnetic, now turns negative, which is why you see the connected correlator being strongly blue, turning negative here. Whereas these bonds here, the antiferromagnetic bonds, are weakened on the horizontal side, and this was characteristic for the single polaron that we have. If we correct for the sign of those changes, we can actually measure the size of the polaron. So here are these connected correlators, sign corrected, showing you how these correlations around the impurity for different distances are changed. And you see how this actually gives you the size of this object, basically the polaron. Now, as you increase doping, again, you see this changes around 20 to 30% doping. The red actually here part, which meant actually weakening of the antiferromagnetic correlations, turns into blue turns into strengthening of the antiferromagnetic correlations into something we would expect actually from a Fermi liquid. So these are the change in correlations that you would actually see from a Fermi liquid. Again, you see it's completely different than what we have in the polaron system. And again, the change happening around 20 to 30% change in the system. To be a bit more quantitative, we can look at these numbers, these specific spin-spin-hole correlators, the connected correlators as a function of doping. And you can really see this sign change. Now here's the polaron regime. And the sign change going over into the Fermi liquid regime happening around 20 to 30% doping. And for large doping, we get actually the pink line, good agreement with the kind of Fermi liquid theory. Okay, and we can see this continuous crossover from the system, from the polaron to the correlations of the Fermi liquid in the system. Okay, final point. Let's do it. The most complex is the whole spin-spin correlator. So we're asking now, if we find two holes next to each other, how are the spins, again, the magnetic environment, how is the spin environment changed? And from early DMRG calculations, also in the TJ model, what people found, and I apologize if I misreference this here, again, this is the first time I talk about this, so this has to be brushed up with the right references. But what people found is that when you have a bound hole pair, you actually find the diagonal correlator in between to be have strongly singlet character, be very strongly antiferromagnetically oriented. And if you look at our and actually the above the hole, like a horizontal hole pair, you find actually this this antiferromagnetic correlations to be strengthened, whereas the adjacent ones to be weakened. And you see actually in the experiment, so this is theory, TJ model, and this is the experiment. And you indeed see again this interesting feature that around 30% doping, we indeed see this maximum strengthening of this singlet bond on the diagonal between the holes that we're seeing here, which we actually would expect also from this bound TJ pair in the system. And then turning over into correlations here where this is weakened, but something that we expect actually also from the Fermi liquid behavior in the system. Okay, yes, and quantitatively we can look at this. Let's just do this quantitative again. The connected correlator plot, which is basically the whole spin correlations minus the bare antiferromagnetic background minus what you would expect if you have two independent polarons. So basically this connected correlator again tells you how much are the correlations modified because of really these two polarons being not separate entities, these two holes not being two separate objects. And you can indeed see that there is actually, again, a strong dependence on the doping. And here's doping. Here's this diagonal correlator as a function of having the holes aligned like this. You see it starts out at 0, then it turns negative, and then it actually turns positive again, the pink line again being the Fermi liquid result. If we go to higher temperatures, you see this vanishes. These are the red data points. So you have to go to reasonably low data points to see this dip. And I guess if we would go to even lower temperatures, we should see this becoming even stronger. The gray line is exact diagonalization, which probably overestimates the dip because of finite size effects. But again, I think you see this, again, the fourth hint that around this 30% doping, you see this change in behavior from polaron behavior to Fermi liquid behavior in the system. Again, all of our indicators, all of the correlation functions point to this transition at about 25 to 30% doping in the system. Okay, I think that's basically what I wanted to tell. I just summarized these latest results where we look at the dope 2D Fermi Hubbard model, continuous doping from 0 to 90% doping, and I think we have a pretty clear picture that we see a breakdown, a complete change in the nature of quasi-particles in the system from polaron behavior. We see the spin susceptibility shows a distinct difference here at 30%, the spin density wave I showed you, and also the singlet character I showed you. All right, yes, that's all I wanted to say just on this one topic today, Fermi Hubbard model. We have a lot of other stuff going on in Munich in our labs on equilibrium dynamics, systems with magnetic fields, gauge fields. I didn't have time to talk about today, but I thought, this was one thing I wanted to share with you today in this talk. And this couldn't have been done, you know, with a wonderful set of collaborators we've been working with and people, you know, doing really the experiments. I should especially highlight Yannis Köpsel. So he's been the driving force also on this latest analysis of experiments. Christian has been leading the experiment. He's now a professor in Tübingen University. And we have the two new postdocs, Sarah and Dominic. Jaya did the spin charge separation. And Mim is the current senior postdoc. The new one just arrived, Thomas Chalopin from Jean Dalibar's group. Guillaume left us for a position in Hamburg. And this has been done together with wonderful theory collaborators, Eugene Demler, Fabian Grust, and Annabel Gott. And with that, I leave you and thank you very much for your attention and leave you with this nice picture from Munich. Thank you.
Thank you, Manuel. Thank you very much for sharing your new results. It's really impressive as usual. You know, beautiful data. Now we're opening the session for questions. So I invite you to raise your hand, or you can post the question on the chat window, and I'll ask the question to the speaker for you. So Daniel Komsky has a question. Oh, what happened? All right.
I just went out of the,
yep.
I think I have to go to screen sharing mode again. I just jumped out of my, wait a moment.
All right.
And share the screen.
Please go ahead. Oh, you're muted, sorry. Now. Daniel? We cannot hear you.
Okay, now I can yes, I can see my microphone. Okay, first very short comment, in a sense historical comment. If you allow me, two questions. A historical comment that is the story of Hall moving in antiferromagnetic background in Hubbard model and leaving trace of wrong spins with confinement. It goes back much earlier than what you referred to, 89. But it was at least 20 years ago we did it more or less same thing with Bulaevsky and Nagaev. But okay, fine, that's historical thing. But from that time, I had a question. Consider the Hall moving in antiferromagnetic background, of course not 1D, 1D is in that sense not interesting, 2D, leaving a trace of wrong spin, making back and forth, returning more or less back to its origin. Now, it's you can call it polaron, you can call it maybe just the block with very diffuse boundaries. Question, suppose I put my Hall at origin of coordinate x equals 0, and I measure experimentally, you can do it now experimentally, nearest neighbor spin correlation function si plus 1, not diagonal, just linear, away from Hall in the center of the Hall. Away is just regular antiferromagnetic. If you approach to the center of the Hall, it becomes modular less and less and less. Question, what it is in the center? Does it become ferromagnetic or it's simply reduced antiferromagnetic? Or if its core is ferromagnetic like Nagaoka ferromagnetism, or it is still antiferromagnetic, close to the center. Or it may depend on the, I don't know, some parameters of T over U or whatever.
Yes, so I mean, maybe let me try to say what we actually did. One thing that we did was maybe it's related to what you're asking. We were pinning the impurity to one position. So usually the
no, you have to allow to move it. You can't pin it. You have to put it as a beginning of coordinate, allow to move it, and then to measure spin-spin correlation function away from the center of the Hall and approaching the center of the Hall.
But then you're doing
original position, not Hall because it moves, but approaching this original position.
We didn't do that experiment. So I think what you would expect to do is if you start to fix the Hole initially at some position, then you would, I think what you would start to see is that the polaron forms, or what you call the diffuse spin bag around it, application. And so that would form, it would be, of course, some excitations or some thermal excitations would be generated. And this object would then delocalize in the system.
But it will delocalize in a different time scale. I mean, just it will move, Hall will move in the time scale of T, and it will delocalize much, much lower.
No, I think there was a nice recent experiment from Marcus, which looked at that, where he looked just at the hole, basically how the hole moves, and that should move. The polaron should move on the scale of exchange coupling.
Yeah, but this hole inside polaron or away from polaron moves at the scale of t. So between t and j, that's my question.
Yes, so I think initially what you would see, initial spreading of the hole would be t, and then after the polaron has formed, then this whole now quasi-particle will then spread with exchange with j.
Exactly. What is the magnetic structure inside this quasi-particle, close to the center of this quasi-particle? Is it antiferromagnetic still, or it is ferromagnetic, like core is Nagaoka, like ferromagnetism? That's the question.
Well, I think it would be like what you see here, the radius extension. Of course, this radius becomes basically infinite in the limit, what you're asking in the limit, if J exchange coupling goes to 0, then the radius of this object would go to infinity, of course.
Yeah, but the core is still antiferromagnetic or ferromagnetic? I mean, just linear along the bond correlation function. Will it close to the core?
Well, it would be ferromagnetic, but
ferro or antiferro?
Yes. So it should be ferro, it should be Nagaoka, but the problem is, of course, for any experiment to measure that, the critical temperature of that state would be so low that we could never measure that.
I think in your previous slide, you have shown the slide with diagonal coupling, but can you show the previous one?
This one?
Yeah, here. Here you see that all the bonds are still antiferromagnetic, close to the center, not really ferromagnetic. They don't change sign. So there is no ferromagnetic hole in the center, in the core.
If I
look at this one, there is no ferromagnetic hole in the core.
Yes, that's right. But I think that depends on the T/J value that you will.
Yeah, that's my question. That's essentially my question.
We cannot.
Whether it depends on T/J or what?
I think so. We cannot tune T/J so much because you see also the dependence of the radius of this object is very weak in T/J. It's a third root
I know.
Root. So, I like your question, but as an experimentalist, I have to say we don't have so much tunability on this. Even if we tune T/J by a factor of 100, we don't gain so much in the size of this object.
Very fair. The answer is that you don't know yet. Okay, very good. Now, a second question is to this crossover to Fermi liquid-like behavior. Yes, I remember that if you do rather simple approximation, simply something like Hubbard 1 or so on, then this question is maybe related. Suppose I start with strong mode insulator and start to dope it. I start to dope my holes in lower Hubbard subband. Initially, sign of hole constant will be positive. It will be holes. But sooner or later, it will become negative. That's very known, old problems, very well known in high TCs. When you dope it, when do you go from the whole sign of positive hole to Fermi liquid-like negative hole? And the simple approximation, if I remember correctly, give you something like 0.3. So it's very similar to what you see. So what do you think? Is it related really to this question of sign of hole coefficient? Or is it a different story?
I don't know. You tell me. I mean, we are an experiment. We just measure correlation functions, and now we can compare to your theory. And we have, I think what I want to say that the higher we go in the correlation functions, the more distinguishing we become to different theories.
Yeah, but crossover to from hole-like behavior with very low hole doping, as a sign of hole coefficient should be definitely positive. To Fermi liquid-like behavior, where sign of hole coefficient should be definitely negative. So the crossover, theoretically in simple approximation, occurs somewhere at around 0.3. So it resembles very much what you see. Maybe it's related. I'm not sure, but that's my question.
Well, that's very interesting. We should get it. We should stay in contact and discuss this. So if you can, yeah. So maybe
to come to Munich. Well, I'm in Köln, but I can't go anywhere now.
But we can phone and Zoom, so we can stay in contact virtually. Yes, very interesting.
Thank you.
Thank you for raising the point.
Thank you.
All right. The next question is from Subir Sachdev.
Oh, hi. Nice talk, Immanuel. Actually, before I ask my question, I do have a comment on Daniel's question. In the cuprates, the Hall coefficient doesn't go from negative to positive or positive to negative. It goes from Hall coefficient density P to density 1 plus P, where P is the density of holes. But okay, and that's what's observed, and there are many theories for that. So my questions are, Immanuel, can you show the second to last transparency on the crossover from?
You mean this
kind of summary of everything? Yeah, the next one. There you go. Yeah, so there's various criteria in here. One is polaron breakdown. The other, for example, is the spin density wave, which I see. Do these crossovers between the two regimes happen roughly the same doping, or they?
Yes, I think what we see. That was kind of the message that I tried to say. At least we see signatures. You know, the different, that's the spin-spin correlator allows us to measure spin structure factor and spin susceptibility. The whole spin-spin correlator allows us to measure how, you know, basically the polaron structure factor, structure. And then we have this other thing, this 4-point correlator, which is again another observable, which is like what's the singlet character between two holes, which people have looked at.
But the thing that can be measured in condensed matter with greater precision is the spin density wave.
Yes.
And that becomes incommensurate already at rather low doping. But I guess you're seeing this happen in around 0.2 or 0.3. Where do you see that happen?
Yeah, so I think we see it happening again. Also, if you look here around between 0.2 and 0.3, this starts to break up. I think, you know, we are not claiming to see stripe phases or something. I don't.
No. The right-hand side is a large Fermi surface.
Exactly. This is Fermi surface. Exactly. This is Fermi liquid behavior. But of course, it's interesting that the question is, of course, at lower temperatures, does this pi 0 or 0 pi that you get from the Fermi liquid, does that have anything to do with the stripe phase?
Oh, no, I don't think so. No.
You don't think
the stripe phase is a property of the low doping region. It's a much longer wavelength where things are incommensurate. So, I mean, I think you have a spin density wave, which is maybe some indication of a large Fermi surface. And on the undoped side, well, maybe it's more like the electron doped rather than the hole doped. But in any case, it would be very interesting to see if this transition between commensurate, incommensurate here and the polaron breakdown happen at exactly the same doping. You think they do, or?
Pretty much. I mean, it's hard to say exactly what you mean by exactly. I mean, if I look here, the susceptibility clearly is at 30%. There's this kind of.
Well, that's the ferromagnetic susceptibility. I'm not sure that's such a.
Right. But then the other correlators change sign also between 20 and 30%. It's of course hard to now pinpoint this exactly, but most of the action, or also here in the 3-point correlator, this is starting to change between 20 and 30%. You know, this is where this thing changes. And also the 4-point correlator pretty much at the same. So I don't think I think what we can say between about 25 and 30%, that's where the action happens in all of those quantities.
Okay, thank you.
I think you're muted, Adrian.
I'm sorry, you're right. So the next question is from Bert Halpern.
Okay, this is just a minor question. When you measure the ferromagnetic susceptibility, you say you're getting it from the correlation function, and of course there's certainly a direct relation between the correlation function and the ferromagnetic susceptibility at when the temperature is high. Do you have to worry about quantum fluctuations destroying that in your case, or are you protected by symmetry or something?
Well, okay, as far as I understand, so what we're measuring at the q equals 0 or close to q equals 0 wave vector, the susceptibility, and of course renormalizing, taking temperature into account, but temperature is basically constant in these experiments. So the chi-s wouldn't change as a function of temperature. Even if we scale it, it would just change the absolute value. So we just measure the spin fluctuations in that finite region of space, in the large finite region of space. So we really measure the spin fluctuation. So the sum of the SZ squares.
Thank you.
All right. There are a couple of questions in the chat window. So one is from Isaac Perez Castillo, or Isaac, who's asking, experimentally, can you introduce vibrations in your optical lattice?
So phonon, I'm probably more directed towards phonon. So that's pretty much not there in our case. So our lattices are pretty static. So we just generate maybe, well, if you would say deficiency or feature, depending on what you want to look at. You can introduce phonons by having another species, a bosonic bath, for example, that would allow for phonons to be coupled in the system. Or if you put systems in a cavity, make these lattices in cavities, then you can have something like phonons in the system. But a priori, we don't have any phonons in the system.
All right, and there's two details about the experiments from Teresa Paiva. What is the value of U over T in the experiments? And
so
yeah,
U over T is 8 typically.
And the temperature in units of the hopping or
in hopping, it's about 0.4.
Mm-hmm.
U over T. T over T, sorry, T over T.
Right.
T over small t.
Perfect. Do we have any other questions from the audience? Actually, my questions were already asked, so well, if no other questions, then let's thank Immanuel one more time, and thank you all for attending today. Next week we have Joel Moore on Wednesday, and hoping to see you there. Have a nice week.
Bye-bye, everybody.
Thank you, Immanuel.
Bye.
Bye.